Good day, everyone. Welcome to the Marine and Offshore webinar on Meteocean hydrodynamics and mooring of floating units. My name is Jose Esteve, and I will be your host today. I am market leader for offshore gas and power based in Paris, and I am accompanied by Guillaume Diot-Cloc, our head of hydrodynamics and Meteocean section of our research department, and by Claire-Julie Frelot, who is head of hydrodynamics and mooring section of our design appraisal department. Together, they will take you through the intricacies of today's webinar. If you've run across some or all of the terms that you see on the screen when discussing with your counterparts or colleagues in offshore floating projects, and you are uncertain of their meaning or the calculations linked to them, then this is your webinar. If you would like to know more, we invite you to check our guidance notes NI 691 and 638, together with a range of rules and guidance notes in our website. You will also find these slides available for download on the bottom left corner of your screen. Questions can be posted on your right-hand side, and we will answer as many as we can at the end of this webinar. Finally, this webinar is being recorded and will be available for download in a couple of days from our website. Today, Guillaume will start with an introduction to the general concepts to set the basis for the discussion. Claire-Julie will then briefly introduce the different types of Meteocean data that can be used for the assessment of floating units, followed by Guillaume's explanation on the different types of analysis and the available simulation tools. Finally, Claire-Julie will summarize it all up with examples of analysis that combine the Meteocean data needed and the tools required. Guillaume, the floor is all yours.
Hello, everyone. So we will start by a few general concepts that are linked to floating structures. So first, what are the objectives of analysis? So we want the structure to be safe, and with regards to extremes, that is to say, is the structure able to withstand extreme environmental conditions, and to know what is the failure probability. We also want to ensure that the structural fatigue life of the units is large enough, and of course larger than its design life. You can have also some question about the operability of the units, that is to say, what is the uptime, what is the available window for maintenance of operation. And these three kind of calculation have associated challenges. So for instance, for extremes, we can, the challenge is that it's by definition rare events, so that we will need some statistical extrapolation, because we want to design for events that have been unobserved, which leads to long simulation time. Extreme, we also have large environmental loads, so the physics is more complex. You have non-linearities that can be challenging as well. On the fatigue side, it's also a long-term assessment. You need to simulate long enough to be able to represent accurately your long-term environments, and there is also quite large uncertainty in the capacity, which is not the topic of this webinar. So what are the environmental loads that the structure should withstand? So of course, something specific to floating units needs is the waves. So the waves, we can distinguish different kind of effects. So the main one is what we call the linear waves, with wave frequency typically between 5 and 20 seconds. So it's the wave that you can see from any ship visually. The wave also induce some low frequency loads, which are called second order loads, or QTF, like quadratic transfer function, and it's much slower. Typically, it's above 20 seconds, and those kind of loads will be relevant to catenary mode units, which have quite slow resonance frequency. On the other hand, you also have high frequency loads, so below 5 seconds, which will be relevant to stiffly moored units such as TLPs. The wind will also be relevant to the design of floating structure. So you have sustained wind condition that will cause some constant force on the structure, but there is also transient wind conditions and turbulence, which can induce some dynamic effect. And finally, there is the currents that will induce loads on the hull and on the mooring lines. Then a bit of vocabulary when designing a floating unit. There is the word long-term analysis or short-term analysis, and here I want you just to specify a bit more what it is. So when we say long-term, it refers to duration that are typically in years. So for instance, in shipping, we design with the 25 years return period. In renewable, it's more the 50 years, and in offshore, we have also the 100 years, which is quite standard. And the fatigue life is also something which is typically comparable to the. So on the top right figure, you see the significant wave heights a long time, so in years. So it's a long duration. And on the other hand, short-term analysis, it refers to analysis that are made on a stable environmental condition. So this time it's typically in hours. So on the right bottom figure, you see wave elevation, but this time it's instantaneous wave elevation, and the time scale is in seconds. So you have 1 hour of wave elevation on this graph. And of course, the short-term analysis is a necessary step to have long-term quantities such as extreme or fatigue life. Then something also specific to floating structure on waves in particular is the randomness. Because the waves, they are generally specified as with a wave spectrum. So for instance, if you have heard about the name John Swap, so John Swap is a kind of wave spectrum, which is parameterized by characteristic value for the wave height, so the significant wave height, and a peak period. So the wave spectrum, it represents where is the wave energy in terms of in frequency. So the peak period is, for instance, the frequency for which, or the period for which you have the most energy, as you see an example on the left figure. But if you want to convert this wave spectrum to a particular time domain realization, there is an infinity of time traces that corresponds to this single wave spectrum. So on the right, you have 4 examples of realization of this wave spectrum, and I've pinpointed for each of those simulations the maximum. And we see that the maximum across the simulation is not the same. So here we have, four simulations depicted, and each of them are called in the jargon, it's called a seed. So if you have 4 seeds, it means that you have made 4 simulations with the same inputs in terms of wave spectrum, just that the phase of the waves have changed. So with this, I want to emphasize that the maximum over duration is not constant. So here I've drawn 4 seeds, and on each of them, the maximum is not the same. So the 1 hour maximum, for instance, is not a single value, it's a random variable. So if I collect all the maximum from each of the seeds, and I do quite a lot of them, I can plot a histogram of this 1 hour maximum, and then the figure that I will get is the figure on the right, which is the histogram of the 1 hour maximum wave height. So it's not a single value, it's a distribution. But then in the standards, we refer to 1 hour maximum or NPM or this kind of thing. And then those value, it's a characteristic value of the distribution. So here on the figure, the red curve is the probability density, and we pinpoint some of the characteristic points. So for instance, the NPM, or which means most probable maximum, is the points where the probability density is the highest. But we could characterize the distribution by other values. So for instance, by value at a given quantile that you can see on the blue curve, which is the cumulative probability distribution. So I will not go into the detail, but it's just to emphasize that the randomness of the waves, and then on the load and the response of the floating structures. So now that we have defined the objective and some quantities, Claire-Julie will switch to the description of the Meteocean data, which will be the inputs required for the simulation and the design assessment.
Hello, everyone. So I will introduce you to the different type of Meteocean data that you can find when you work on this kind of projects. So we can find 3 main types of data. So in-cast data, scatter diagrams, and extreme data. The in-cast data is the main source of data. And then we can extrapolate scatter diagram and extreme data from this in-cast data. So first, I will explain what are in-cast data. So in-cast data are a list of consecutive sea states that can be computed from a model, computation model, or measured on a site. So we will have a list every 1 hour or every 3 hours or maybe every 6 hours of the wave, wind, and current on this site. So most of the time we will find waves that can be swells, that can be wind seas, that can be both, and the parameters of this wave spectrum. We will also have the wind speed and the heading of the speed. And same for the current speed and heading of the current. So the in-cast data, it can be 6 months of data, and it can be up to 50 years of data. It really depends on the model that was used and the measurement on site. What is it used for? So in-cast data can be used for several kinds of study. For example, for mooring fatigue analysis. In that case, we can use the data as it is, meaning using all the sea states in this data. Or if we have too many sea states in the data and it would be too time consuming to run them all, it can be clustered in groups of similar sea states to reduce the number of simulations. We can also use in-cast data when we perform hydrodynamic spectral long-term analysis. We have to be careful when we use in-cast data because, as I said, it can be 6 months of data or it can be 50 years. The results of the analysis will depend on this length of data. Because if you want to perform a fatigue analysis for a unit that will remain on site for 20 years, maybe using only 1 year on data is not accurate enough. You might miss the highest environment. We can have a big contribution to the damage on the unit. And if you want to compute an extreme response, for example, a 100-year return period in a spectral long-term analysis, it will be much more accurate if you use 10 years of data than if you use 1 year. Then the scatter diagrams. So the scatter diagram are extracted from in-cast data. This is a table that gives the probability for a couple of parameters. So for example, we can have a table that gives the wave height versus the wave peak period, or the wave height versus the wave heading, wind speed versus wind heading, etc. Here on the slide, you can see a scatter diagram for wind speed versus direction and current speed versus direction. So the scatter diagrams can be used for the same kind of study than in cast data. It is the same data, just represented on other way. So the difference is that when you have scatter diagrams, you don't have the correlation between wind waves and currents. So we will have to combine these scatter diagrams to recreate realistic sea states. Same as for the in-cast data, it is possible to cluster some sea states to limit the number of computations. So we can use this data for mooring fatigue or for hydrodynamic analysis. Then the extreme data. So extreme data are an extrapolation from the in-cast data. You can see on the graph, you have the blue dots that are the in-cast data. And then we make an extrapolation to compute the extreme return period. For example, here you can see the light gray dot. It's a 100-year return period, meaning it's a sea state that will occur every 10 minus 2 with a probability of 10 minus 2 each year. So for extreme data, most of the time in your Meteocean report, you will find the wave height for different return periods, commonly 100, 50, 10, and 1 year. The associated spectrum for the wave, directional spreading sometimes, the partitioning between swell and wind speed. For wind data, also the wind speed for different return periods, the associated spectrum. You can find for some specific cases, for example, when you want a Meteocean data for floating offshore wind turbine, the turbulence intensity. And for some places in the world, like West Africa, squall time series. And then we have the current data with the extreme return period for the speed and the current profile. We can also find sometimes in the report the correlation between the parameters, meaning if I have a 100 return period of waves, what will the wind be? Because we will not likely have at the same time a 100-year return period for wave, wind, and current. It would be highly improbable. So we can find these correlations in the report. And if it's not available, BV rules NR 493 in Appendix 2, we can find guidance to help recreate this correlation. Here on the slide, the example for extratropical conditions with a correlation between the intensity of the parameter, meaning the wave height, wind speed, and current speed, and the correlation between the wind direction, wave direction, and current direction. So this extreme data can be used for several kinds of study, for example, extreme mooring analysis, extreme calculations for floating offshore wind turbine, hydrodynamic analysis, sloshing analysis also. So this is the different kind of data you can find for Meteocean data. And now I will leave Guillaume to explain you the different simulation type and tools that we can use for these studies.
Yeah, thank you, Claire. So now that we know on which environment we should simulate the behavior of the units, I will go into the detail about the simulation that we can do. So I will start by the, let's say, the basic and generally the first step when you assess a floating structure, which is so-called linear sea keeping. So it aims at evaluating the response of large floating structure on water waves. It's almost systematically performed because nowadays it's there is a lot of commercial tools available and it's well mastered. So example of some such software are WAMIT, Aqua, Diodor, and of course Hydrostar, which is developed in Bureau Veritas. So to set up this kind of simulation, in terms of engineering time, it's let's say between 1 hour to a day, depending on the complexity of the geometry. And it also allows CPU time, and you generally have everything that you need in less than 30 minutes. So what are the inputs and outputs of such code? So the input is simply the hull geometry given as a discretized geometry, so surface mesh, and mass property. And the output will be some hydrodynamic characteristic of the geometry, so the famous added mass, wave damping, or excitation forces. And maybe more interestingly for the user, the so-called RAOs. So RAOs, it means response amplitude operator, but we could also call that a transfer function. So it can be a transfer function of motion, acceleration, pressure, hull girder loads. And on the graph on the bottom right, you see a transfer function of heave of a floating unit. So just to try to explain quickly what is a transfer function is how much the units react to unitary waves. So for instance, if on this curve, if you have a wave at whatever the direction for this kind of units, at 0.5 radian per second, if the input wave is 1 meter, the response in heave will be 1.6. And it's a linear model, that is to say that if you double the wave amplitude, you will also double the response. And with this simplification, everything is easy in terms of engineering, because you can do some spectral analysis to combine this transfer function with the description of the environment in terms of wave spectrum. And then, with this spectral analysis, the distribution of the maximum, so the distribution that I was showing before, is known analytically. So you do not need to make a lot of simulation. You know perfectly the shape of the distribution. And it follows that the long-term statistics are also straightforward to derive, and then it's basically cheap to calculate any statistic that you like with this kind of model. And you have the response to linear wave. So with this sea-keeping model, you have basically motions, but also pressure and hull girder loads. If you want to go further, and for instance, to get stress in the structure of your hull, you will need to do a so-called hydrostructure analysis. That is to say, you need to transfer the pressure from the wave, which is calculated by a sea-keeping model, to a structural finite element model. So in Bureau Veritas, it would be done by Homer. So in top of the input needed for the hydrodynamic analysis, you will need a finite element mesh. And the output will be transfer function, but this time transfer function of stresses, of stresses in the hull. And this is typically used for spectral fatigue analysis, for instance. Then the mode units, unfortunately, linear waves are not their only concerns, and there is other loads that act on this on the mooring and that are relevant. So we can cite the wind loads, the currents, and also the nonlinear waves like second order, or also viscous drag on small parts of the structure. The mooring will also react in a nonlinear way, so that the linear spectral analysis is not sufficient to have a comprehensive modeling of mode units. So we need to integrate all the cited loads in a more comprehensive model, which will have to be in a time domain. So example of such mooring software are OrcaFlex, DeepLines, FlexCom, and of course in Bureau Veritas, Ariane and Opera. Within each time domain software, you will find many options, and those options will correspond to different assumptions made on the physics that you want to model. So, for instance, you can choose to solve at the same time the wave frequency and the low frequency. You can choose to decouple them. You can choose to use line dynamics or only quasi-statics model for the moving lines. So there is a large variety of options which will impact quite dramatically the simulation time. So with the simplest assumption, you can have a simulation of 3 hours in a few seconds. And it is sufficient for quite a number of applications. On the other hand, if you want to include all the physics, if you want to have the line dynamic, if you want to couple all the different loads between the structure, between the mooring lines, the wind, etc., the calculation time will be on the other way around. It will be more hours of CPU time to calculate only minutes of real scale. So I will not go into the detail of each assumption. I will just illustrate one, which is the coupling of the mooring lines dynamic with the floater motions. So here I've taken 2 examples. So in example A, where you have a large floating structure and relatively light mooring lines compared to the mass of the floater. So it will be maybe typical of a big FPSO. And in such a case, the mass of the line will not affect the motion of the units. So you can solve the motion of the units without accounting for the mass of the line, which allows to model the line with simplified model, quasi-static model, and it allows for much faster simulation. On the other hand, if we look at the structure B, the structure B is smaller, and then the mass of the lines is not negligible compared to the one of the floater. And then the mass of the line will alter the motion of the floater, and of course the floater will alter the motion of the line. So you cannot calculate them separately, and you need to have a coupled simulation. So while in A, you could solve the floater motion and then solve the line dynamics separately. So we see that there is different options that can be turned on in simulation mode, and then you also have the options to couple the different options as well. So in time domain simulation, there is a wide variety of assumptions available, and then the choice is a compromise between the accuracy of a given assumption for a given model and the calculation cost. The problem is that if you say, okay, I want to be safe, I put all the options on, then the calculation will be large, and you will not be able to do as much seed as you might want. So you would do some approximation on the statistical side. So the best compromise, it actually depends on the physical properties of the system. So for instance, the resonance frequency of the system are quite important to know to know if you need to account for the low frequency waves for the vertical motion, for instance. The dimensions of the floater compared to the wavelengths is important as well. And then as I was mentioning just before, the mass of the line compared to the floater is also an important parameter to choose the option. Then taking a step back, just an illustration of a typical workflow to calculate a floating structure. So we generally start by a linear sea-keeping model, which on its own will be able to calculate the response due to waves. So you will have motion, acceleration, pressure, altogether loads. All this you can have only with a linear sea-keeping model. Then if you want to have stresses on a finite element structure, you will need to use hydrostructure tools such as Homer in Bureau Veritas. And then if you want to account for waves, wind, and currents, and if you are interested in getting line tension or to study the station keeping, you will need to use a time domain mooring software such as Opera and Ariane. And then if the wind and waves have effect on the structure, there is a need to use both mooring with hydrostructural groups. And I will give back the floor to Claire-Julie to provide some example of analysis.
Thank you, Guillaume. So to sum up, some example of really simple analysis to see how to do it. So, for example, an hydrodynamic analysis for an FPSO. So the objective of the study will be to compute the extreme response for motion, acceleration, bending moment, shear forces, relative wave elevation for different load gates of this FPSO. So what type of Meteocean data will we use in that case? So the easiest way would be to use extreme Meteocean data. We have extreme Meteocean data, you use them in the computation, it gives you an extreme response. Easiest way. When we don't have extreme Meteocean data, we can use in-case data. But in that case, we don't input extreme cases, so we don't have an extreme response. And we will need to extrapolate this response to reach the extreme response of the system. So it adds an extrapolation phase in the calculation. The type of calculation methodology, frequency domain analysis, is the more commonly used methodology for this kind of study, like using HydroStar. For an extreme mooring analysis, so the objective of the study in that case would be to compute the extreme tension at different points of the line, mainly at the fairlead, at the anchors, and the different connectors along the line. We would also compute the extreme offsets of the unit. This computation for both intact and damaged mooring system cases. So in that case, we need to use extreme Meteocean data because we want extreme response. The best way to do this is to perform a time domain analysis. And depending on the complexity of the system, we use different modeling, meaning do we need to couple the line and the floater? Is it a wind turbine when we also need to couple the turbine and the floater? Or is it a basic FPSO for which we can do several assumptions to simplify the model? Depending on this, we can use different softwares, like Ariane 8 for the most simple systems and Opera for the most complex ones. And then fatigue mooring analysis. So in this case, the objective of the study is to compute the damage in the mooring lines to determine the acceptable design life of the unit. So for this kind of study, we can use both scatter diagram or in-case data. Still, we have to be cautious to use a length of data sufficient to have accurate results. The best method is to use time domain calculation. And same as earlier for the extreme, the software to be used will depend on the complexity of the system. Some frequency domain methodology can sometimes be used. For us in Bureau Veritas, we consider this as really a first approach during a pre-project analysis because we find it to be less accurate than time domain. So it can be used in pre-project, but this will not be acceptable at the design stage, the final design stage of the unit. So this is the end of the presentation, and now we will be available to answer your questions.
Thank you very much, Claire-Julie and Guillaume, for your very detailed presentation. So we have some questions that have come to us. So I will be then directing to you. We have one relating to floating offshore wind turbines. It goes like this. Is the method to correlate the wind waves parameter accurate or satisfactory enough for designing floating wind turbines when such parameters are clearly design driving? Are direct measurements advised or imposed instead? Claire-Julie, is something that you can answer?
Yes. So, of course, we can always use the guidance that are provided in BV rules. These guidance are defined to be what we call conservative, meaning that when you use them, your results will tend to be always on the highest side. This can lead to be a little over, lead to a little over design, meaning you will maybe use more strength line or more solid floater. So, but you will always be on the safe side when you use this data. Of course, if this correlation is very designing and you want to have a design as accurate as possible, then it's better to have a clearly correlation that comes from measurement. But in any case, we can use the guidance note.
Thank you very much, Julie. I have a question from Matthew Lewin. He says, you talked about a couple analyses for hull motions and moorings where the mooring system may influence the motions of the hull. Have you carried out a couple analyses that also includes the effects of the load from the turbine where these may also influence the motions of the hull and also the moorings? How CPU hungry would such an analysis be? Is there something that you will be able to answer, Claire-Julie or Guillaume? I don't know.
It will be more for me. So yes, we have performed this kind of analysis. When we are involved in certifying an offshore wind turbine, we do what we call an integrated load analysis. That is an analysis to compute the different loads in the unit, like the bending at different parts of the system, the tension in lines. And for this, we use a fully coupled model, meaning our model couples the lines, the floater, and the turbine. We use Opera to do this kind of analysis, and it can be quite time consuming because it's really a complex system. So we can use some simplification on some cases. For example, for the extreme analysis, we can do some simplification on the turbine, not for the fatigue. It can be quite time consuming, like I would say something like 4 to 5 hours to compute 1 hour of a real sea state.
Thank you, Claire-Julie. I think I have a question for you, Guillaume. It says, I've seen mention 10 to minus 8.7 or 10 to minus 5 probability levels in past BV rules. What does this refer to?
So this probabilities refers to the probability in terms of wave cycles. So in modern rules, we prefer to have the target probabilities in terms of return period like 100 years because it's more explicit. But before and still sometimes there is a probability in terms of wave on probability cycles. So if you convert 10 to the power minus 8.7 in terms of duration, considering the cycle duration, which is around the wave cycle, which will be around 10 seconds, then you fall back to 100 years. So it's another way to define the extremes, which was used before lots, and now we prefer to specify things in years, which is more consistent because different loads can have different cycle duration, and then the number of cycles in a given duration can depend on the loads that you are looking at.
Okay, thank you very much, Guillaume. I think I have another question for you, Claire-Julie. Does BV require a minimum number of seats
Yes, we indeed require a minimum number of seeds. So for oil and gas, for example, in DV NR493, we require at least 5 seeds because, as Guillaume explained, the time series of wave elevation generated from one spectrum can be completely different from one to the other. It's randomly generated. So you can have a nice seed, meaning the wave will be pretty mild, and you can have a very severe seed with very high waves with the same spectrum sometimes. So to take into account this randomness and not take the risk of missing a critical seed state just because the seed was nice, we asked to use at least 5.
Okay, thank you very much. We are receiving many more questions now. It's difficult to choose the one that have here from Rodrigo Matos. Okay, I will read it out loud. When trying to simply describe the local wave condition in a period of 1 to 5 years, if 10 years is not available, without extrapolating the data to extreme conditions, what additional information can be inferred from the scatter diagram? I think once again, Claire-Julie, this is for you.
So if I understand correctly, the question is how you can find 1 to 5 years return period when you don't have the extreme in your report. So in that case, maybe I can go back to the slide. Here. So in that case, you can find by yourself your 1 or 5 year return period of data by plotting your scatter diagram, like the blue dots here. Then you can fit an extrapolation on it, and on this extrapolation, you can target the probability that you want, and then you will have your return period. So yeah, you can extract directly the return period from the scatter diagram that you have. If you are doing a hydrodynamic analysis, you might want to not extrapolate the Meteocean data, but extrapolate the results. In that case, you will perform a long-term analysis, spectral analysis for the hydrodynamic. You will have the answers for each point of your scatter diagram, and you will do this extrapolation on the answer and find your 5 years response.
Thanks again, Claire-Julie. And I think I have one question that is repeated twice. Again, I think it's for you, Claire-Julie. On the, do we always have to do time domain analysis for mooring calculations, or when do we opt between frequency and time domain approach?
Generally, time domain is always more accurate for mooring analysis. Spectral analysis, as I said, for fatigue can be used really as a pre-project, but it's less accurate than time domain because it doesn't take all the parameters into account.
Thank you, Claire-Julie. Guillaume, I have a question for you. If you could briefly explain the differences between our new Opera software and the Ariane software.
Yes, of course. So I was mentioning that different time domain software can have a variety of assumptions, and between Opera and Ariane, both cannot do the, Ariane cannot do the full scope of analysis. So for instance, with Ariane, you cannot couple the line dynamics with the motion of the floater. And with Opera, you can do that. So you can solve at the same time the motion of the line, the dynamic of the lines, and the dynamic of the floater at the same time. So all what you can do with Ariane, you can do with Opera, but not the other way around.
Okay, and I have one last question for you, Guillaume, once again regarding to the software. How is the nonlinear behavior of the mooring lines model?
So, so if I read fully the question, it asks if Hydrostar can include this. So now in frequency domain, we cannot include the nonlinearity of the mooring system. In frequency domain, what we can have is only a linearized linear mooring, so which is generally not sufficient for actual mooring lines. So to model mooring lines and their nonlinear behavior, we need to go into time domain, either in Ariane or in Opera. And then you can have the nonlinear behavior of the mooring line. Okay. Then there is different model. You can have quasi-static, and then you can have also a dynamic 2D, 3D. There is many way of modeling the line. And again, each time a compromise between accuracy and CPU cost.
Thank you very much. Now I think we've reached the end of our webinar today. Thank you very much to our experts, Claire-Julie Frelot and Guillaume Hautecloque, for the very insightful details on the hydrodynamics, Meteocean, and mooring for floating units. Thank you very much for all those that have been watching us. I remind you that this webinar is being recorded and can be available to watch in a couple of days from our website. And the slides presented to you are available for download directly in your screen, and will also be available at our website. Thank you very much. Have a great day ahead. Looking forward to see you in the next webinar.
Thank you.
Thank you.